Welcome back, everyone. This is our last talk for the today's session. So we have Jason Saied from Rogers. He will talk about Alcove walk formula for SSV polynomials. Please, Jason.
Thank you. Yeah, so thank you to all of you for coming. I know this is an inconvenient hour for a lot of you, so it's really great that you were able to show up. And thanks again to the organizers for the invitation. So today I want to talk about an Alcove walk formula for SSV polynomials. This is the name that I'm giving to the functions, the quasi-polynomials that Siddharth introduced on Tuesday. And I'm hoping that by giving this Alcove walk formula, we can make them a lot more concrete and accessible for all of you to study and help us understand them better. So first, let's set some of the background. Really, SSV polynomials are a generalization of Whittaker functions. So let me remind you what these are, although I know we've heard about them already at this conference. So let's say we have some reductive group G over a non-Archimedean local field. And if you like, as always, you can think of GLN over the p-adics. Then the Iwahori Whittaker functions are certain functions on this group with invariance properties with respect to the Iwahori and the unipotent subgroups. You can construct them in a nice way from a principal series representation of G. What Brubaker, Bump, and Licata showed, prompted by Bogdan-Ion, is that you can recover values of these Iwahori Whittaker functions from Q limits of Macdonald polynomials. And that makes them relevant to all of us, since we're here to study Macdonald polynomials. But there's a further generalization of these Whittaker functions that's also of interest. These arise in the study of metaplectic covers of the group, the finite degree covers that are no longer algebraic groups, but they have interesting number theoretic properties. And in this setting, you can also define Iwahori Whittaker functions. And so it's a natural question to ask, do these correspond to some type of Macdonald polynomial? And the answer is yes. They're the polynomials that Siddharth discussed on Tuesday, and we're going to look more closely at them today. And to help keep everything more concrete, we're going to deal in type A. So SSV polynomials are family E mu upper n, where mu is some integer weight and n is a positive integer. These were introduced in 2019 by Sahi, Stokman, and Venkateswaran. And they depend on many parameters. First, they're functions of x, and then they have the two Macdonald parameters q and k, and also a new family of parameters, these g's. These g's are really coming from the metaplectic side. In the Whittaker functions, there are certain Gauss sums that can be slightly generalized even in that setting to parameters. And here we'll just treat them as parameters for the SSV polynomials. The connection with the things we already understand is that if n equals 1, we get the non-symmetric Macdonald polynomial. And in the q limits, when q goes to 0, or also when q goes to infinity, we recover certain values of metaplectic Iwahori Whittaker functions. So what we're going to study today, for the most part, is actually a slight generalization of this. This was, again, discussed in Siddharth's talk on Tuesday. We have new quasi-polynomials E zeta, where zeta is a real tuple rather than an integer weight like for the original setting. And the conversion between the two of these is that if we take a fractional mu, if we take E mu over n, then this is going to recover the original SSV polynomial. But really, the results are more nicely stated for these quasi-polynomials, so we'll mostly stick to those. Any questions so far? Please feel free to interrupt. Okay. So like I said at the beginning, our goal today is to give an Alcove walk formula for these polynomials. So we'll write each E mu, where mu is now a real tuple rather than an integer one, as a sum over Alcove walks with coefficients that I'll give explicitly later. And all of the powers of x that appear are very concretely known. They all come from applying some Weyl group element, the end of the Alcove walk, to a fixed m of mu that's determined by our original mu. And this is the unique point that's in the fundamental alcove and is Weyl conjugate to mu. So in the setting of Ram and Yip, which this is a direct generalization of for Macdonald polynomials, m of mu is always taken to be 0. So here we're generalizing this slightly and just working with any point in the fundamental alcove. And these produce the rest of the SSV polynomials. So that was the introduction. Now we'll give some basic standard notation for type A root systems and all that. Then I'll introduce you to Alcove walks and SSV polynomials. And finally, we'll conclude with the Alcove walk formula and a bunch of applications of it. So first, let me just throw up the usual notation. I'm sure you've all seen this 100 times today. So we'll only work in type A. So we'll fix some positive integer r corresponding to GLR. We have RR being our Euclidean space with orthonormal basis, the epsilon, and our inner product is this round bracket. I won't read all the notation to you because you've seen it already. The only things worth pointing out here is, first of all, the P, the weight lattice, is the GLR weight lattice. So it's the integer tuples. That's the setting we're working in. And second, I denote the finite Weyl group by W0. Just W is going to be reserved for the affine Weyl group because that's the one that comes up the most often. And of course, we have the affine versions of all of this. So I'll just put a subscript A on the Euclidean space to say that this is the extended space where we add our usual extra basis vector delta, and we extend our form by saying that delta pairs with everything to 0. So then we have the affine roots. And here I'm only interested in the real roots because they're the ones you can reflect through. So they're the roots of the form something finite plus some integer multiple of delta. And of course, we have the positive ones, which are just the positive finite roots plus anything with a positive multiple of delta, and our new simple root alpha 0. So now that we have these two spaces, we have the pairing between the extended and the Euclidean space by saying take the form of the Euclidean parts and add the multiple of delta that you have here. Okay, so that's our basic setting. And now that we have this form, we can very neatly define hyperplanes for each affine root. So H alpha hat is just all the elements of the Euclidean space on which alpha hat vanishes with respect to that pairing. And S alpha hat is the reflection through that hyperplane. This is the setting in which we'll think of our Weyl group, and this will give us our Alcoves. So an example just to visualize the way we're going to think about all of this, and these pictures are very similar to the pictures in Ram and Yip's original paper. Here we'll study the GL3 case, so type A2, and we'll project our picture to the span of alpha 1 and alpha 2, these two blue arrows. So in this setting, all of these black lines and also the colorful lines are hyperplanes corresponding to different affine roots. So this lower pink line is the hyperplane corresponding to the highest root. And if we shift up by 1, that's h of alpha 0 or delta minus theta. So using these hyperplanes, we cut up the plane into these triangles, or really they're simplices if we include the third dimension. So as I already alluded to, we'll just think of our affine Weyl group as being the reflections in all of these affine root hyperplanes. And we'll think of it mostly as a Coxeter group generated by the SIs, the reflections in the simple roots. Of course, we have the usual alternative presentation of the affine Weyl group as translations by elements of the root lattice, semi-direct product with the finite Weyl group. I want to point out here that I'm choosing not to extend this, even though I'm studying GLN. I'm not using the weight lattice here, because I do want my Weyl group to be a Coxeter group. You can do this in that greater generality, but for what we need, it's not necessary. And so W here is set up to naturally act on the Euclidean space, but of course we have the contragradient action on the extended space. And so I'll use this star notation to denote the action on the extended space, and no notation to be the action on the Euclidean space. Okay, so then the alcoves for our alcove walks are just the connected components of the Euclidean space minus all of these affine root hyperplanes. In the picture I showed before, they were the triangles. And I'll show another picture in a second. Our favorite alcove, the fundamental alcove, is the alcove that's positive with respect to all of the simple roots. So alpha IV is greater than 0 for all I. And since we're in GLN, I might as well state that concretely. We can think of the fundamental alcove as the decreasing tuples where the greatest difference is less than 1. And what's nice about the set of alcoves is that the affine Weyl group acts simply transitively on that set. What that allows us to do is to identify alcoves with the Weyl group element that takes you there. So here again is our same GL3 setting projected to this two-dimensional subspace. And we can say this one is the fundamental alcove, and every other alcove is labeled by what it would take to get there. So this one is a translation of the fundamental alcove. So this is the translation by theta, and so on for all the other points. So whenever I write down an alcove, really I'm going to write down its Weyl group element. So now that we have alcoves, we can start walking across them. Let's take some Weyl group W and fix a reduced expression for it, SI1 up to SIL. So then an alcove walk of that type, where the type depends on this sequence of indices, so it does care about the choice of reduced expression. So such an alcove walk is a sequence of alcoves, and for the purposes of this talk, we assume they start at 1, and then they proceed to some other alcoves, and we'll call that last one the end of P. The defining conditions for being an alcove walk is that in each step, either it's the same as the previous step, which we call a fold, or they're adjacent to one another. But we don't just want them to be adjacent. We need this adjacency to know something about this Weyl group element that we started with. So in particular, what we say is that AJ is AJ minus 1 times SIJ. We're here, remember, we're interpreting this alcove as a Weyl group element. So this is right multiplication of that Weyl group element by Sij. And we call this a crossing. And if you haven't thought about this before, it might not be clear why this condition means that they are adjacent to one another. So let me just write that out a little more clearly. The point is that if AJ minus 1 multiplied by Sij, you can commute that to the left. So we're reflecting in the hyperplane where AJ minus 1 sends alpha ij. And it makes sense that this is a wall of the AJ minus 1 hyperplane because alpha ij, its hyperplane borders the fundamental alcove. So then when you move everything by AJ minus 1, you should take that hyperplane to a wall of AJ minus 1. And we're reflecting over that wall to get to AJ. Any questions so far? Okay. So let's look at a few examples to make sure we understand how this works. So we'll first look at an unfolded alcove walk of type W being 0, 1, 2, 0. And in this talk, we'll always start at the fundamental alcove. So what this means is that our Weyl group element is the product according to these indices, S0, S1, S2, S0. And if we're not folding, then in each step, we start here and then we proceed. We write multiply by S0, then we write multiply by S1, by S2, by S0. So these are what our crossings look like. And here you can see that they are in fact adjacent to one another, the way you'd like. And again, algebraically, we just represent this by continuing to right multiply by the next thing in the sequence. So I want to recall the notation. We said that the end of P is the element corresponding to its final alcove. So here, the end of P is just W. And later on, we'll need the notation, the weight of a path, and the finite part. So the point is that since the Weyl group element is a semi-direct product, you can write the end of P as some translation times some finite part. And we'll just separate those out. So you're translating by the weight, alpha 1 plus 2 alpha 2, and the finite part is S1, S2. So let's look at an example that does have folds. Here we'll fold in positions 1 and 3. And what this is telling me, and we're working with the same type, same Weyl group element, is that in position 1, I should choose to do nothing, right? That's what it means to fold, is I don't right multiply by the corresponding element of W's reduced expression. So I start at 1, and then I stay at 1. And this is represented by going up to the hyperplane you're supposed to cross, and then turning around. Really, you can think about it as draw the alcove walk as if you did cross, and then reflect the tail over that hyperplane. That's where this folding imagery comes from. And then we do cross in the next step. So we do multiply by S1. We choose not to cross at S2, so we do nothing. And that's why there's another bend here. And then we do S0. And in this case, again, we can calculate the endpoint to be S1, S0. And it has this decomposition as a translation by alpha 2. And S1, S2 is the final part. Any questions? Okay. One more very quickly, because I want to emphasize that alcove walks can double back on themselves. So they're not determined by their endpoint. So for the same type, if I choose to fold in the second and third spots, I lose the S1 and the S2. So I do S0, I fold twice, doing nothing, and then I come back to the fundamental alcove. So my endpoint is just 1. This tells me that the terms in my alcove walk formula are not going to all be different powers of x. So we can get a 1 coming in multiple different ways. But what is true, if you think about the way we got these alcove walks, is that they correspond to what I'll call subwords of W. So what I mean here more rigorously is we can fix a reduced expression for W, and then consider all the words that we get by omitting some elements of that reduced expression. So here we omit the S1 and the S2. And if you know the terminology, really, you can see that the set of alcove walks corresponds to the Bruhat order. Everything less than W in the Bruhat order, those will be the endpoints that you get. And if you pay attention to the word, you can get not just the endpoint, but the alcove walk. We'll revisit this later. So one last piece of alcove walk terminology that I'll need is the orientation. So just as in Ram and Yip, we're going to try to assign a plus and negative side to each hyperplane. And what we can do concretely is we can say for each finite hyperplane corresponding to some finite alpha, the positive side is the side with the fundamental alcove on it. And the negative side is the other side. So for this alpha 2, you can see I circled this plus because this is where the fundamental alcove is. And the minus is the other side. For every other hyperplane, every alpha plus some multiple of delta, the orientation is just parallel. We just shift it over. So you can see at the top here, for all these hyperplanes parallel to alpha 2, it's just minus plus, minus plus, minus plus. So this orientation lets us put a sign on a fold. So whenever the fold is reflected over a particular hyperplane, it takes on the sign of that hyperplane there. So here we fold at the alpha 2 hyperplane and we're on the positive side. So we say this is a positive fold. Similarly, for our second fold in this walk, we fold here at the 2 delta minus theta hyperplane, and that's the negative side of that. So we would call this a negative fold. So now that we have all of that set up, we can finally set up the space of SSV polynomials that Siddharth introduced us to on Tuesday. We have a bunch of parameters here. First, we have the two Macdonald parameters, Q and K, and you probably call K the square root of T. And then we have these G parameters, GS for S being a real number. And really, there's fewer parameters than that. These conditions reduce how many there are, but it's nice to have this notation for all reals. So first, we really only determine our parameters modulo 1. So if you have, and further, if you have an integer, the G0, that's going to be K. So in the integer case, all of these G's are going to go away, and that's how we're going to get Macdonald polynomials. Further, we say that GS and G minus S are inverses, as long as S is not in the integer. So then we can take our field, which is just the complex numbers extended by these various parameters. In practice, for any particular quasi-polynomial we're interested in, we'll only need finitely many of these G's to show up, and Siddharth was talking about this, but we might as well just throw them all into the field for what we are doing now. And the space of interest, the space in which the SSV polynomials live, we'll call the space of Laurent quasi-polynomials over F. It's just the formal span of the symbols x to the mu, where mu is a real weight, a real tuple of integers.
Sorry, what do you mean by that? Is congruent to T modulo 1? Everything is real here.
Yeah, so I should have written this as S minus T is an integer. So these are real numbers.
Awesome.
Any other questions? Okay. Thank you for the question. Okay, so now we have the space of quasi-polynomials set up, and this is where our SSV quasi-polynomials will live. So the following results are due to Sahi, Stokman, and Venkateswaran, and these will set up our polynomials. So what they really did is they produced a new representation of the double affine Hecke algebra. And concretely, what this gives us is it gives us the family of Y operators, Y nu hat, where nu hat is some affine weight. And these act not on the space of Laurent polynomials, but on the space of Laurent quasi-polynomials. And these Y operators are exactly what will give us our SSVs. What they showed is that the Y operators are simultaneously diagonalizable with eigenvectors that we'll call E mu for every real tuple mu, with specified eigenvalues, gamma, that I'll give explicitly later because they'll show up in the Alcove walk formula. And further, as a normalization condition, we assume that x mu is coefficient 1 in the monomial expansion of E mu. So these eigenvectors are what we'll call the SSV quasi-polynomials. Or most of the time, I'll forget to say quasi and just say SSV polynomials. And the way that they arise, the fact that they come from, eigenfunctions of the y's, just like Macdonald polynomials, is what makes them accessible to study. And this is what lets us do the Alcove walk formula. In particular, the same intertwiners, tau I, appearing in, say, the paper of Ram and Yip, they still work here. So these are some elements of the double affine Hecke algebra, or the extended double affine Hecke algebra. And if you map them through this new Daha representation to the SSV, they will now intertwine SSV polynomials rather than just Macdonald polynomials. And by this tilde, all I mean is these are equal up to some non-zero scalar that I don't feel like writing down, but we could write down explicitly if we care. So now that we have this set up and we know what SSV polynomials are, let's look at a few examples. First of all, if mu is an integer, then E mu is the corresponding Macdonald polynomial. This is good to know. This lets us tie things back to what we knew before. The point is that all of the G parameters are going to go away, and we're just acting on the space of Laurent polynomials rather than quasi-polynomials. So everything is as you already know. So the new stuff is whenever mu is not just integers. So what I want to show first is what I'll call a generalized one-box formula. And looking for this was suggested to me by Arun Ram. It's very similar to a result that he's written down. So if we have a tuple that's just a C in one spot and a 0 in all the others, where here C is between 0 and 1, then the SSV polynomial has this very nice form. So its leading term is xi to the c, and the lower terms is just some ugly looking scalar times a sum of the lower xi. Where here the sigma function that shows up, sigma of c, is just going to be k inverse if you have a positive integer, k if it's non-positive, and a g otherwise. So the Macdonald case, giving the formula that you might have seen before, it was written down, for example, in the recent paper of Ram and Yip. This sigma would be a k inverse. And so these would cancel, and this would be a k to the 2r minus 2i. And this precisely matches the formula that's written there.
I have a brief question. In this formula, is sigma of, because you stated C, you're restricted in this from 0 to 1, right? But below you write down this general formula. So does this formula extend to arbitrary real value of C, or?
Oh, yes, it does. So yeah, in this case, I wanted C to be small just because otherwise this one box formula wouldn't hold. You would need a lot more terms. But yes, this sigma will appear elsewhere. So I wanted to define it for all C.
All right, okay. But this formula only holds for C small, like written.
Yeah, good point. Yeah, so here I should have just written that if C is 1, you get K inverse, otherwise it's a G. But on the next slide, sigma will appear again, so I wanted to define it. Okay, and one other example, and this is really the most important example of all, is that if lambda is in the closure of the fundamental alcove, then you can check very straightforwardly that E lambda is just X lambda. It's just a monomial. And this is the key to everything, because this lets us take the intertwiners and get any SSV polynomial. So in the paper of Ram and Yip, the analog of this is that E0 equals 1. Right, and from there you apply the intertwiners and you can get anything you want. And so here, since we already know that any element out there in the Euclidean space is Weyl conjugate to something in the closed fundamental alcove, we just have to find what that is, that monomial, and then apply the appropriate intertwiners to get from E lambda to E mu. And so we can actually take Ram and Yip's expansion for the product of intertwiners, apply it to X lambda, and interpret what all of that means in the light of this new, more general representation. And what we get is the Alcove walk formula.
But can I ask here, what's the eigenvalue of yi on x to the lambda if you're in the interior of this alcove?
So it's a little messy. I'll show it here. Ignore everything else, but I'll give it explicitly in a minute.
Oh, okay, it's coming. Okay, thanks.
Yeah, sure, no problem. But it's not as nice to write down as, you know, this power of q times that power of t. It's a little more gross. But okay, yeah. So let's fix our mu, and let's, like before, let m of mu be the unique element that's in the Weyl orbit of mu and in the closed fundamental alcove. So this is the starting point for our recursion. And we'll let w be the shortest element that takes you from m of mu to mu. So this reduced expression for w tells us exactly the sequence of intertwiners you need to apply to get from x lambda to mu, to E mu. So then we know that E mu is up to a scalar that we can know explicitly, the product of these intertwiners applied to x to the m mu. So as I said, all we need to do is expand this product and then see what happens when we apply it to this monomial. And so this formula looks a little gross, but all the pieces can actually be understood very nicely and explicitly. So first of all, it's a sum over all Alcove walks of type W. These powers, like I said before, they all come from applying the endpoint of some Alcove walk to this one fixed power m of mu. And this is the same one in the fundamental Alcove. Then we have some product of these sigma functions. So you might recall that sigma is always k, k inverse, or g. So this is fairly explicit and we can deal with this. In the original Ram and Yip formula, we can write this more nicely as just a power of k. But here, because of the g's, we have to break it up a little bit. And then we have a product of positive folds and negative folds. And in each case, we have some quotient involving the eigenvalue of the y operator on x to the m of mu. And this formula is given below. Inside this formula, we have these beta j's that appear, and these are precisely the same as in Ram and Yip. The way you can get them concretely is by taking an Alcove walk of type W inverse and writing down the hyperplanes that it crosses. So the positive roots corresponding to those hyperplanes are exactly these beta j's. And as Arun was asking, so this gamma can be written down in this form. What's notable about the form of this gamma is that it's some positive power of q times a product of sigmas that we can write down in detail when we need it. So just this level of detail is going to be enough for us to see some nice consequences of the Alcove walk formula. But before I continue, are there any questions about this? Okay, so let's look briefly at an example so I can maybe convince you this isn't so bad. Let's consider a non-integer mu. Let's say mu is 2, 4/3, 0. So we can write mu if we apply the right vowel group elements. We can write it as 4/3, 1, 1, an element of the fundamental alcove with S0, S1 applied to it. So our W is this S0, S1, and M of mu is this element of the fundamental alcove. So then we need to write down what those betas are. And so as described, we can take this blue path of type W inverse, and we see that first you'll cross the alpha 1 hyperplane. And then, because you're supposed to do an S0, you won't cross the alpha 0 hyperplane, but you'll cross S1 of alpha 0. So in other words, you take the alpha 0 hyperplane, you reflect it over alpha 1, and you get this. And so that lets us write down these betas that appear in the eigenvalues. And then using this formula, you can calculate explicitly these gammas. So if we want to look at a particular term in this Alcove walk formula, since W has length 2, it will have 2 to the 2, so 4 terms. So we can pick one of them, say this orange one, where we fold in the first position and then cross in the second. So this Alcove walk has endpoint, which is also equal to its finite part. It's just S1. And so the term looks like this on the left-hand side. So it's x to the end applied to m of mu, some sigma. There's only one of them because phi of p is length 1. And then this factor coming from the fact that we have a negative fold. And if we pop in the values that we calculated, the sigma is g 1/3. S1 of m of mu is like this. And here's our gamma. So once we've done this calculation once, calculating the other terms is straightforward. We just use the same eigenvalues everywhere, although we will have to recalculate the sigmas. But so even this, maybe you're not convinced, maybe this seems a little ugly. So we'll spend some more time talking about applications of this formula and how this helps us get a handle on SSV polynomials. So first of all, we can talk about triangularity. As I alluded to before, let's recall the Bruhat order on the affine Bio group. The most concrete way to write it down, and the way that's relevant for what we're doing right now, is to say, let's take U2, let's fix a reduced expression for U2. Then the elements that are less than U2 is everything you can get by omitting some of the SIs from U2's reduced expression. And of course, you'll recall that this is very similar to what is happening with Alcove walks. And then we can import this Bruhat order on W over to the Euclidean space. We can just say that for some lambda in the fundamental alcove, U1 lambda is less than U2 lambda, if and only if those Weyl group elements, U1 is less than U2 in the Bruhat order. So different Weyl orbits are not comparable, but that won't come up. So then what we can see, and this was first observed by Sahi, Stokman, and Venkateswaran, although they didn't use the Alcove walk formula, is that E mu is equal to x to the mu plus lower terms in this ordering. And I wanted to write this down just because it's so immediate from the way the Alcove walk formula is written. Our leading term, mu, is W applied to M of mu, where remember W is defined to be the shortest thing, taking M of mu as mu. And then if we look back at the formula, all the other monomials that show up are precisely the endpoint of some Alcove walk applied to M of mu. And like we said, the way you would get some Alcove walk, some endpoint, is by taking an element, by taking the reduced expression and omitting stuff, omitting SIs, which is precisely the everything less than W in the Bruhat order. So triangularity falls out immediately. Any questions so far? Okay. So what's nice about this is we can actually improve this triangularity a little bit. So I've been calling this full triangularity. And the point is that not only do we have this triangularity result, but also all of those C nus are known to be non-zero. So we know precisely which powers of X are going to appear in our SSV polynomial. And I don't know who first proved this result, but I know that Siddharth has a proof of it in the Macdonald case. But so the idea here is that in our Alcove walk formula, of course, all of these terms are going to show up. But possibly there's some cancellation. Possibly when we add things together, you'll lose some of these terms. But it turns out that if we specialize our parameters appropriately, then all the coefficients are going to be strictly positive. So no cancellation is possible. And we can again see this very concretely just playing with the Alcove walk formula. So if we look back at it, everything here is with no signs, a product of sigmas, k inverse minus k's, and then either gamma or 1 over 1 minus gamma. So we know concretely which factors we have to think about. So what we can do if we want positivity is just throw away all those g's. So the sigmas get a lot simpler. And then say that k is between 0 and 1. Just anything between 0 and 1. So that makes all of these sigmas positive numbers. And it makes k inverse minus k positive because k is small. So for positivity, we just have to make sure that gamma is between 0 and 1. That'll keep both of these positive. And we can get away with this because gamma is some positive power of q times the product of sigmas that we can disregard because we set all the k's and g is equal to 1 or something positive. So for each beta j, if you take q close enough to 0 and positive, you can get gamma in the desired region. And you just do this for all j. There's only finitely many of them that are relevant to you at a particular time. You can get them all between 0 and 1. So what that means is that we have positivity and there's no cancellation. So we can precisely characterize the powers that show up in E mu.
easy to enumerate the number of terms that will contribute to a given nu?
I am not sure, actually. That would be interesting to know. But there should be a lot of them in general, because the Alcove walk formula has 2 to the length of W number of terms, and there are only this many terms that show up. But no, sorry, I don't have an answer for that. Any other questions?
Hi, sorry, I have a question. So when you mean this full triangularity, the C nu are polynomials, perhaps rational functions of the parameters like the G and the K. Is that right?
Right. And
So so when you say non-zero, you just mean those are not trivial polynomials. Like they might
Yes.
still be zero for some values of the. I see.
Oh, I see. Yeah, okay, that could be misleading. Yes, absolutely. For example, many of them will vanish if you set K equal to 1.
I see. Yeah, no, that makes sense. But so what you're saying is that there is a choice so that they are all positive
Right.
at the
Yeah,
same time. Great, thank you.
no problem. Thanks for helping me clarify.
So can we compare this with this the classical ones? So if you take mu from integers or rationals.
Yeah, so if mu is all integers, then that's the Macdonald setting. What about it?
No, is there any relation between? So does it make sense to like take in some limit of mu?
Hmm.
So say mu has a rational, real coefficients,
Mhm.
and then I want to approximate with the rational coefficients. Does it make sense?
Sort of. I mean, so if you're in any particular alcove, like if you're looking at 2 mu's that are in the interior of the same alcove, then their formulas are going to look nearly identical because you're just applying the same sequence of intertwiners to 2 points in the fundamental alcove that are very close. But I don't know how I would write that down rigorously because the G's would need to be transformed a bit. So I don't have a precise result, but they should look similar. I wouldn't want to say anything about limits because if we try to take a sequence of these SSVs that approach some wall, some hyperplane, then you could jump, right? Because it might take only 5 intertwiners to get to some point, but once you go up to a hyperplane, it could take 6 to get there. So I wouldn't say that these are continuous or anything like that.
Okay.
But one way to compare these to the regular Macdonald polynomials is actually on the next slide. So let's talk about that. So the original way that SSV polynomials were written down was not for all real tuples, but rather for these E mu n's. And these again are the polynomials that will specialize to metaplectic Whittaker functions. So these are worth studying as their own special case. And these can be written down as just E mu over n, so they're fractional things. And we inflate the powers so that we get a polynomial rather than a quasi-polynomial. And of course, everything we said applies to these E mu n's, just specialize appropriately. So what's nice, if you write down enough examples, you'll see that as n increases, you seem to get something that looks kind of similar, but with fewer terms. And so what you can prove just by messing around with the full triangularity and the Bruhat order is that if m divides n, then the monomials that appear in E mu n are a subset of the monomials appearing in E mu m. So the way I like to think about this is that E mu n has fewer terms than the corresponding Macdonald polynomial. They'll get a little, they'll look different. They'll have these G parameters showing up, but you have strictly fewer. And so this is a nice result to compare them. Really what's happening here, if you think about it in the fractional case, is where we're looking at some array, right? We have some E mu, and as you pull mu back toward the origin, you're going to have fewer and fewer terms because the walk to get there is shorter. But so we can say this precisely, we can say which terms show up.
And this is for arbitrary, these big G, these couplings or constants.
Yes, yeah,
Or not?
the G parameters can be arbitrary, but is that what you're asking?
Yeah, yeah, exactly. So you did not introduce any dependence on n there.
Right.
Okay.
Yeah, I mean, the G's are often rewritten in terms of the n, and that's how you'll see it in my paper or in Siddhartha's first paper. But yeah, really, you can use the same G's as before. It's fine. Okay, so now that we know some of that, we can also look at the Q limit formulas. And this is, again, interesting because the Q limits are what give us Whittaker functions. But in this Alcove walk formula, Q only appears in a few very easily understood spots. In particular, it's only in these gamma eigenvalue factors. And in those factors, Q always has a positive exponent. So the only ways that gamma can appear is if you have a negative fold, then it's gamma over 1 minus gamma. And if you have a positive fold, it's just 1 over 1 minus gamma. So if Q goes to 0 or Q goes to infinity, these will all limit to nice things, right? If we look at negative folds, Q goes to 0, this just goes away. Q goes to infinity, you get a negative 1. And similar with the positive folds. So if we take the Q limits of the SSV polynomials, we get these much simpler formulas to look at, where now the sum is over this, in the 0 case, it's over Alcove walks that only have positive folds. Anything with a negative fold has coefficient 0. And the same product of sigma is the same x, but the more complicated eigenvalue quotient is just replaced with k inverse minus k to the number of folds. And very similarly, in the Q goes to infinity case, we have Alcove walks with only negative folds. So this is very nice because we can write this as an Alcove walk formula for metaplectic Iwahori Whittaker functions. And I talked about this at a conference where there were many people who studied these, and nobody could tell me that they recognized this. So if anybody who does study Whittaker functions recognizes this, I'd love to hear about it. Otherwise, I'm interested to understand if this tells us anything new about metaplectic Whittaker functions that wasn't known before. And of course, we have any other variant you like. If maybe you're interested in studying these permuted basement Macdonald polynomials, well, there's an SSV version. Apply the appropriate Hecke operator. Similarly, we have a symmetrized version where you apply this Hecke symmetrizer. What's interesting about these is that they're not symmetric, like in the Macdonald case. They are chintogonal symmetric. And this makes perfect sense because this chintogonal's Weil group action is really what started this whole thing in the first place. Right? Chintogonals were studying these Whittaker functions, and they produced this interesting Weil group action that Sahi, Stokman, and Venkateswaran wanted to understand. And what they did is they invented this Daha action, the one that gives us SSV polynomials, in order to explain the Weil group action. So it's very natural that using that Daha action to create polynomials will give you something chintogonal symmetric. And we can write this formula down explicitly, just like the symmetric case in the Ram and Yip paper. Similarly, we have an anti-symmetrized version, and this is what will give us spherical Whittaker functions in the metaplectic setting. And again, the formula looks very similar. You just have to adjust the k coefficients. And finally, while we're here, I thought I would mention some work in progress. So one of the first results that was published after the Ram and Yip Alcove walk formula was Yip's Littlewood-Richardson rule. So Yip took a product of two Macdonald polynomials and expanded that as a sum of other Macdonald polynomials. This notation might be slightly misleading. The defect of this formula is that the same Macdonald polynomial comes up multiple times on the right-hand side. So it doesn't perfectly give you the Littlewood-Richardson coefficients, but it's still useful as a product, expanding the product as a sum. And you can do a similar thing in the SSV setting, and that will be out fairly soon. So that's what I wanted to talk about. I thought I would end with some questions I have about SSV polynomials that maybe would get people interested. So first of all, as I already said, we have these new Q-limit Alcove walk formulas for metaplectic Whittaker functions. Does this provide any new insights? Second, an obvious question is, we have the Alcove walk formula. Can we cook up a tableau formula? One promising avenue is to look at the recent work of Ram and Yip, or before that, Lennart, where they took the Alcove walk formula and combined terms and showed how you can get some sort of tableau formula. So it'd be interesting to see if that can happen here. On a similar note, SSV polynomials generalize both metaplectic Whittaker functions and Macdonald polynomials. And both of those families have their own solvable lattice models, right? The Whittaker functions were done this year by Bush-Umis, Bump, Brubaker, and Gustafsson. And the Macdonalds were done by Borden and Wheeler, and later Agarwal. So can we somehow combine these solvable lattice models to get an SSV lattice model? And finally, what other interpretations of SSV polynomials do we have? Pick your favorite talk at this conference. Is there an SSV analog? Let's find out. So that's what I wanted to say. Thank you for your attention today.
Are there any questions?
Maybe I can ask a question, and maybe it's very naive, but I'm new to SSV. I think this is the second talk I heard about this, so I know very little. But I see your list of problems. But in the symmetrized case, are they orthogonal polynomials in some sense? Is that known?
So I don't know of an inner product on SSVs that makes them orthogonal. I think Siddharth might have some results in this direction, but I don't know if he's if they're anywhere yet. Siddharth, do you know the answer to this?
Yeah, so I mean, Jasper, Vidya, and I were writing the second paper, and it's almost done. I know I've been saying this for a while, but it really is almost done. It's like but it's long. So so there should be some sort of bi-orthogonality for these polynomials. So don't expect them to be orthogonal, but maybe some dual family should also be SSV polynomials. I think that's.
Can I ask a question about the C function? So if I square the intertwiner, I get a product of two C functions. Now, with generic values for your G's, like you've chosen just completely random values for your G's, that's going to be mostly garbage. But if it actually comes from the metaplectic,
Arun, I'm sorry, I'm missing what you said.
Yes.
So you're breaking up. Would you
okay, let
mind
me try.
repeating?
So if I square Twiner, I get a product of two C functions. And if with generic G's, that's just some generic ugly expression. But if I use G's that actually come from Gauss sums, is that somehow very nice? Nice.
That's a good question. I am not sure. I would expect that something nice should happen, but I haven't written it out to check. I've been mostly working with the G's as parameters.
So if I may take a crack at that. I'm not sure I completely understood Arun's question, but the intertwiners are, of course, only unique up to pre and post factors of involving the Y operators. If you wish, you can normalize them so that they actually square to 1. And there is some, yeah, you can make some explicit choice involving the Y operator so that the intertwiners square to 1. And then what you get, you should be able to see, because there should be some formula in terms of the y eigenvalues that Jason was writing. Does that answer your question, Arun?
Well, I'm quite keen not to renormalize them so they square to 1, because I want to see the Q-val denominator, for example, that appears in Castleman-Shalaika and some of those features, or the kinds of things that Anna was talking about, where you've got this correction factor M. And I am hoping that is better when you're actually metaplectic than when you're generic.
Okay.
Sorry.
So,
Oh.
sorry. So that's actually that's right. But the fact that you know explicitly how to normalize them so that they square to 1 means that you can compute what you want for any other normalization. Since there is some explicit normalization which makes them square to 1, with some explicit pre and post factor involving the y's for your favorite unnormalized. Therefore, you can calculate and get the C function.
Wait, sorry, which intertwiners are they that square to 1? Sorry.
Well, I don't know, maybe so okay.
Not the y, right? Or I mean,
no, the y's are the eigen operators. So these guys
Right.
are eigen functions for the y's.
yes,
But these
yes.
operators, the intertwiners, which walk you up and down the the family of polynomials, and
Yes, but, I see.
and you can normalize them. So I think that's what Arun was
Right, so
asking.
the tau, right? Like not the,
Yeah.
Yeah, so take the tau
I see.
and multiply by an appropriate function of y's to kill off the denominator. Because we
see.
can multiply by, although
I
I'm
think
not actually sure, Siddharth, I
normally-
think
No, no.
that,
What I'm saying is that you take a tau, and suppose you take 2 polynomials in the y's, arbitrary or even rational functions, and you call this a new intertwiner. Let's call it tau twiddle, where there's a prefactor involving y's and a postfactor involving y's. Okay, now you apply it to one of these polynomials. The first factor will rescale it. The second factor will move, I mean, the tau itself will move it to where you want to go. And then the postfactor, sorry, the prefactor will again scale it. So it's again an intertwiner. So what I'm saying is that intertwiners, just the intertwining property, doesn't care about what you multiply before and after. And there is an appropriate choice. You can either put the factor on the right or the left, so it squares to 1. And now if you want to have something else, it probably differs from this guy, the normalized guy. It differs from it by some y factor. And therefore you can compute its action or its square or something. I don't know. maybe, yeah. Sorry, yeah, that's all I can say.
I just wanted to contribute that normally I like these. So if you take these vectorized elements in terms of, so you form these particular linear combinations of either Hecke and the identity or the Hecke and its inverse, and then you get an R check matrix, and you can easily normalize. So just of a, let's say. So that it has this sort of unitarity condition that R check of U is the inverse of R check of U.
You were lost in between. Can you repeat?
Right. So I was saying basically you can form these vectorized elements, R check of an argument, and you can easily normalize this so that its inverse is obtained by inverting the argument. Now these intertwiners, these are checks evaluated at yi. So if you take R check ii plus 1 and you evaluate this at yi over yi plus 1, and the only thing you have to decide is whether the prefactor, these rational functions, go before or after the Hecke generator. I believe if you put Hecke first and the finite Hecke first, and then the things involving the y's, then this should be the intertwiner that squares to the identity. Anyway, I don't know if it works here as well when you have all these extra parameters, but that's usually an easy way to find it.
So, yeah, I mean, anything that's really about the Daha will work because the Daha didn't change, only the representation did.
Those normalized intertwiners that everyone doesn't like.
I have a question. So do you understand the relationship between the combinatorial formula this produces for Whittaker functions in the or Iwahori Whittaker functions in the limit and some of the existing combinatorial formulas like crystals or Littleman paths or
Right, so I haven't written that out in detail. I think that, I mean, I expect that these should sum to those, similar to how the Alcove formula sums to the Tableau formula. But I haven't written it out. I haven't proven it.
Mhm. And I guess similarly to like the compression formulas of, I think one of Christian Leonard's students. Sidler, I think.
Right, yes. So I expect such results should be there in this setting, but I haven't had time to do them yet.
Mhm. And the other thing is with the stability, I think on a previous slide, maybe page 23. Can you say something about sort of stability in the sense of saying something for any large enough n?
Oh, sorry, you mean this one?
Yes, this one.
Yeah,
Sorry, I
right.
misremembered.
No, that's okay. Yeah, so as long as, once n is large enough that mu over n lives in, some finite Weyl conjugate of the fundamental alcove. So for large enough n, after that, the formula basically isn't going to change. The g parameters will be slightly different because, it's different weights that you're plugging in. But other than that, like the formula will have the same shape. It will have the same number of terms and the same pattern. So I guess probably if you specialize all the g's to 1, then for sufficiently large n, only the x powers would change, I believe.
But what if you specialize the g's to Gauss sums? Do you know if you can recover the stability of the multiple Dirichlet series coefficients? Does that make sense?
That's a good question. I haven't actually studied the multiple Dirichlet series, so I'll have to look into that. That's
so I think for very large n, right, you should just have a finite Weyl orbit of non-zero coefficients well in, in the right thing, which is maybe some sum of these, right? Sorry, clearly my leanings are towards that end, but
anyway. I get what you mean. Yeah, thanks for pointing that out. I'll think about that.
I have a very general question about this. This Alcove formula will help us to understand the restriction. So if you specialize some of the variables to be 1, even in the Macdonald case. So you said something about little bit recursion coefficient. So it helps us to prove that. So what's about restriction? Will it help?
Sorry, you broke up in the middle. It helps us to prove.
So if we restrict and then substitute some other variables to be 1, and then I want to understand that Macdonald polynomial, okay, in terms of that fewer variable Macdonald polynomials. So this Alcove formula, will it help us to give explicit formula?
I mean, it does give something, but I don't know that it will be easy. One comment is that this version of even my Macdonald polynomials, they're maybe backward. If we flip all the variables, then we have something that is stable in the sense that, if you have trailing zeros at the end, then you get the lower Macdonald polynomial. So if let's say we flip all the variables, I am not. So again, I haven't written down anything about specializing to get the lower ones, but that's something I'm thinking about. But this stability property, like, even if we just try trailing zeros for the x's, it doesn't quite work for SSVs. There's something off, even in the symmetric case. So I need to look into that more and see what is true.
Yeah, okay, thanks.
No problem.
Any more questions?
Sorry, so you're specializing some of the variables to 1, not to 0, right? So you're not discussing stability.
Yeah, because I'm trying to understand this from the Demuzur module's point of view. So if you start with the Demuzur module and then assume that it is invariant under some parabolic subalgebra. So I want to restrict to that parabolic subalgebra and then understand its character. So my claim is like if you start with higher level, so affine Demuzur module and then restrict to that particular parabolic subalgebra, it will be sum of again that smaller algebra Demuzur modules.
And that corresponds to specializing variables to 1?
Yeah, specialized to 1, yeah.
Oh.
The stability usually they specialize to 0 and then study, you know, that I'm not talking about.
Yeah, sorry, I misunderstood your original question.
But that is also interesting here in this case, SSV, whether that is true or not, stability.
One thing you could do if you're trying to stabilize, I mean, so I didn't completely understand this, but maybe I can make a suggestion so you can follow through on it. You could, at least in the Jack limit, let's say, so I didn't think through, if you want to specialize some of the variables to 1, what you can do is you can subtract 1 from everything. So in other words, you make a change of it. So you want to specialize something to 1, well, you just look at x minus 1, and then you're specializing something at 0. But the polynomial with 1 subtracted off from the x's, that has an expansion in terms of the Jack polynomials again, using the binomial formula for Kunkov and Olshansky. And we know what are the coefficients that show up in this binomial formula. Those are special values of these interpolation polynomials that I defined. And so, yeah, but the binomial formula is due to Okunkov and Olshansky. So if you do that, then you will at least understand how to specialize some of the xi's to 1. You have to combine these two, plus you use stability.
Okay.
And you're specializing to 0. So you can, do you understand what I'm saying?
Yeah.
Okay, so you subtract 1 and then you plug something equal to 0. And both things are kind of understood, but I just kind of never saw any reason to specialize things to 1. But you know, that's going to give you some answers, maybe useful. And there is also a binomial formula for Macdonald polynomials, which is due to Okunkov alone. And maybe that will help with what you're trying to do. So take a look at it.
Yeah, sure, thanks.
It's a very interesting question.
Any more questions or comments? Okay, if not, let's thank the speaker again.
Thank you everyone for coming.